Imagine being able to see a display device in sharp focus without using eyeglasses, contact lenses, or undergoing surgery. Consider a user without perfect vision. The error in the focusing of light by the user's eye is known from the eyeglasses prescription for most people. We use this data to compute an altered image that, when viewed through a light field display, will appear in sharp focus for this particular individual. Myopic vision has a focal range shorter than the display distance, and this results in the user seeing blurred images. Prior work pre-filters a multi-layer display. The image is in sharp focus, but the contrast is low. A light field approach can address the contrast problem, but has low spatial resolution. Due to spatial angular trade-off of the hardware, we have developed a pre-filtered light field display, which enables the received image to have both high resolution and high contrast. We use a finer lenslet array and have a thinner form factor than the prior light field solution. For the display outside the focal range of the eye, the image is convolved with the kernel, and the retina receives a blurred image. The multi-layer method pre-filtered the image content, so a sharp image is received. But because of the shared pixels, colors are mixed, and the contrast is low. Pamplona et al. Uses a light field display so that each ray is mapped to exactly one view. Due to the number of views required, the received pixel is large, and the resolution is low. Our method also uses a light field display, but since the light field is pre-filtered, the pixels are smaller, and the resolution is higher. For some views, the colors are also mixed, but the contrast problem is reduced due to a higher angular sampling rate. First, we will show some simulated results. An out-of-focus image on a conventional display is blurred. Pamplona et al. Only generated a slightly better image with a constrained hardware requirement. Earlier work, multi-layer display, produces a much sharper image, but the contrast is low. At the same sharpness, our new method provides an image with much higher contrast. To evaluate the combined effect, we use a perceptual metric, HDR VDP2, which provides a differences detection map and a quality score. Here, our results has the highest score. In the second example, our result has 5 times the contrast and more than 3 times the score. And now, here's the final example. For the prototype and experiment, we build a light field display using a parallax barrier on an iPod Touch. The camera generates a -6 diopter hyperoptic eye with a 6 mm diameter pupil. On the right is a blurred scene with a corrected image. Here we show the comparison using a short animation. Notice how sharp the face of the bunny and the background tree. The prototype is also easy to construct, and we will illustrate how to build it in a few seconds. We first show a pre-filtered light field image on display. When viewed by the defocus camera, everything is blurred. Placing a pinhole array mask on top reveals a sharp image after some alignment. The pre-filtering method assumes a fixed distance, but in real life the head can move, and the received image will have ringing artifacts. Solving the inverse problem in the spatial domain enables us to constrain such perturbation. At the original location, the quality decreases slightly, but it remains unaffected across some distance. Here we show the comparison video by constantly changing the distance, and our result is invariant to such movement. Previously, we assumed a single viewing direction. In practice, we may need to account for lateral motion by the viewer. Similar to the depth invariant compensation, we can incorporate lateral motion into our pre-filtering. Here, we show a stereo view of the prototype as an example, where such correction is performed. We see the target video and the capture video without correction on a conventional display. With the pre-filtered light field video on top right, the captured images are much sharper, as shown on the bottom, and the optimization allows 2 eyes separated by a 65 mm distance. Finally, we are also able to correct higher order aberrations. Unlike defocus, higher-order aberrations have non-circular point spread functions. Interestingly, a few of them, such as trefoil, can be corrected with conventional displays, but most cannot. Our method successfully corrects all such aberrations. With our vision-correcting display system, we hope to be able to make a significant impact on the lives of millions of people. The technology proposed in this paper makes the first step towards that goal.